In 7.5, we're going to be talking about inverse circular functions or inverse trig functions. So we've got a lot of things to read to set this up. For a function f, every element x in the domain corresponds to one and only element, or y, in the range. Okay. Think about what we know about function. Remember in the past, this was a function, but this was not a function. In order to be a function, it had to pass the vertical line test. Okay, so think about that. It had to be passing the vertical line test in order to be a function. Okay, so from now on, we're just assuming that we're talking about something that is a function. Okay, something that does pass the vertical line test. If a function is defined so that each range element is used only once, then it is one-to-one. So we've also got this thing called one-to-one. And so if you look back at just your basic parabola, that's not one-to-one. Basically, this is a horizontal line test. Okay, so in order to be an inverse, we're going to have to be a function that is one-to-one. And so something's going to have to pass both the vertical line test and the horizontal line test. Okay? Any horizontal line will intersect the graph of a one-to-one function in at most 1 point. So one-to-one, it's got to pass the horizontal line test. So here's an example of something that does. X cubed passes the horizontal line test, but x squared does not pass the horizontal line test. Okay? The inverse function of the one-to-one function is defined as this, which I think is hard to read. It says all points yx such that the point xy belongs to the function. Basically, you might remember from past classes, college algebra or algebra 2, where we switch x and y. That was how we formed the inverse function in those other classes. So, a word of caution, the -1 is not an exponent. Okay, it gets confusing because if you look at a calculator, your calculator has a button like this. And generally what that does is if you hit the number 4 and you hit that button on your calculator, it just means 4 to the -1st power, which flips it. It makes that 1/4 or 0.25 comes out of your calculator. That is absolutely not what we are doing. Okay, the -1 and like when I say sine -1 x. Okay, I wouldn't say sine -1 of x. Okay, that's not what I would say. That's not an exponent -1. That means inverse. Okay, that means inverse sine. And so be careful and don't call that -1 an exponent. So a summary of inverse functions. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value. That's your vertical line test and horizontal line test. If a function is one-to-one, then f has an inverse function. Okay, so it's kind of important that we're one-to-one. The domain of f is the range of the inverse, and the range of f is the domain of the inverse. Again, that's just reminding us to switch x and y. But we won't really talk about switching x and y. We'll be talking about domain and range. And it's going to be really important to think about the domain and the range of these functions. And I'll give you a chart later, and you'll be able to reference that chart. But it's going to be really important to look at domain and range. The graphs of the function and the inverse are reflections of each other across the line y equal x. And then down here is kind of how to find an inverse of a function. You can look at these 3 steps. But that looks more like what we did in college algebra. We won't be doing a whole lot of that. Okay. So then this next picture, BA is the reflection of AB. Again, they're talking about, in order to find the inverse, you're switching x and y. And here they're talking about the reflection. So if this was your function, they reflected it over the line y equals x to get this inverse function. Okay, that's not something that we will be graphing. We won't be really doing that. They're just trying to set this up and help you understand what an inverse is. Okay. Note, we often restrict the domain of a function that is not one-to-one to make it one-to-one without changing the range. Okay. So basically, when we look back at a function like this that wasn't one-to-one, this doesn't have an inverse. Okay, we can't work with this. We can't work with this, and so we're going to restrict the domain and basically just blank out part of the graph because we don't want it. Okay, we are only going to look at just half of the graph, and so that's when they say restrict the domain. We're only going to look at the right side of it, and so if you only look at the right side of it, then it's like, okay, now it's one-to-one. That's going to be really important for us as we look at trig functions, because if you remember, when we graphed a sine curve looks something like this. That was one period of it, and if you go on the other way, okay, and it goes on and on and on forever. It's periodic, that repeats itself, but it's pretty easy to see that's not going to be one-to-one, and so we're not going to be able to deal with that. That's not going to have an inverse, okay? Except what we're going to do is we're going to restrict the domain, and basically we're only going to look at like that, okay? We're going to restrict it and only look at part of the graph, and if you only look at part of the graph, now it is one-to-one. Okay, now it is one-to-one, and that part is going to have an inverse, and we're going to be able to deal with that. Okay, so that's what that slide was saying. We're going to have to restrict the domain. Inverse sine function. If we look at y equals inverse sine of x, okay, or sometimes it's written as arc sine, what that means is sine of what equals x, okay? Sine of y is going to equal x. So inverse sine is kind of undoing the sine function, I suppose. All right, now you see this and you see this, that range of from negative pi over 2 to positive pi over 2 is going to be really important. In fact, the domain and range are going to be really important in this lesson. And each of the 6 trig functions or inverse trig functions are going to be slightly different. So we're going to have to really pay attention to domain and range. For inverse sine, the domain is from -1 to +1. And its range is from negative pi over 2 to positive pi over 2. Now, occasionally we'll be in degrees, so that would be like from -90 degrees to +90 degrees. But in general, most of the time we're going to be in radians, so we would say from negative pi over 2 to positive pi over 2. Okay? That's going to be really important that you remember those two things. So, I don't know if you want to put a star by those, or circle those, or whatever. Those are going to be really important. X-intercept of the graph is at 0, y-intercept of the graph is at 0, and then this graph is symmetric at the origin, which makes it an odd function. We've talked about odd functions and even functions in the past, but we're talking about inverse sine. Strangely enough, this is the graph of inverse sine. We won't really have to do anything with the graph, but what we can notice is the x values. The domain, that's between -1 and 1, and then the y values, or the range, is between negative pi over 2 and pi over 2. So we can see that domain and range inside that graph. But we don't really have to graph anything. You're going to need to be able to understand that domain is -1 to 1 and range is from negative pi over 2 to plus pi. So when we do these examples, the examples are really pretty quick. Okay, they're really pretty quick, but it is important to keep in mind the domain and the range. So we just talked about that. The domain for inverse sine is from -1 to 1, and the range for inverse sine is from negative pi over 2 to positive pi over 2. Okay? Now, a couple things to remember for domain. That I don't think a very good definition for domain is the x numbers. I know that's what everybody says. When I say, what's domain, you'll say the x numbers. And that's kind of true, but that's a very limited definition. I think a better way of thinking about it as the inputs. Okay? Domain is talking about the input values, or what you're allowed to plug in. And the range is the output, or what will come out. Okay, what your answer would be, I suppose. Okay? So domain is input, range is output. Also with the range,
negative pi over 2 to positive pi over 2. We all should know that pi over 2 is up here, like 90 degrees. Okay? So negative pi over 2 would be down here. That's like negative 90 degrees. And so when it says that the range is from negative pi over 2 to positive pi over 2, it's talking about from here to here, basically. Or, in other words, they're talking about quadrants 1 and 4. So your takeaway should be this, okay? The positive value is going to be in quadrant 1, and a negative value is going to be in quadrant 4, okay? We're going to have to think about what and where. And so what is going to come from the chart usually. Where, if it's positive, it's in quadrant 1, and if it's negative, it's in quadrant 4. Okay. So when we look at a problem like part A, example A, it's going to look really simple because we do arc sine or inverse sine, and we can look at the chart, and we've done this before. We do inverse sine, and so we find the sine and we find the 1/2, and we use the chart backwards. And if we use the chart backwards, we're going to arrive at an angle of pi over 6. Okay? Pi over 6. That feels like we've done that before. Okay? But that's the what. All right? That's the what. The where is kind of subtle. But when you're looking at this input value of 1/2 and seeing that that's a positive number, then you would come over here and say, well, positive numbers are going to be located in the inverse quadrant. And so I'm just talking about pi over 6 in the first quadrant. And so pi over 6 in the first quadrant just is what it is. And so this answer is pi over 6. I realize it feels like I talked over this problem for way too much for such an easy problem. You use the chart backwards, you get pi over 6. That's it. Some of these problems are a lot more complicated than that. Okay? When we look at inverse sine of -1, inverse sine of -1, okay? Just treat it like a 1, first of all. But if I look at my chart, an inverse sine and a 1, that's leading you to an angle of pi over 2, right? Pi over 2. That is the what. But then you come over here and say, well, negative. Okay, negative means that my angle is in the fourth quadrant. And so what you're going to want to do is you're going to want to put a pi over 2 here. Okay? And it's very tempting to do what we've done in the past chapters and go all the way around here. Did I say pi over 2? I guess that's not where pi over 2 is. I'm sorry. It's tempting to say negative pi over 2 is right here. So it's tempting for people to go all the way around and to call that 3 pi over 2. Okay? But 3 pi over 2 is not in the range. Okay? 3 pi over 2 is not in the range. The acceptable interval, or the acceptable range, is from negative pi over 2 to positive pi over 2. And so I think a better way of looking at this one is when you have this range, ask yourself the question, am I even allowed to have a negative answer? Am I allowed to have a negative answer? If you're allowed to have a negative answer, then this is just going to be negative pi over 2. That won't always be the case because all of the trig functions won't have negative answers. It's impossible. Okay? That one is. So the what, I get the pi over 2 from the chart, and the where, I know this is in the fourth quadrant. That negative right there tells me that we're going to be in the fourth quadrant. And I know I can have a negative answer in the fourth quadrant. Negative pi over 2. Okay. Now, part C, inverse sine of -2. Okay? And that's not on the chart, I suppose, so that's your first problem you're looking at. But also notice your domain. Remember how the domain was from -1 to 1? That's talking about input values. That's talking about what I am even allowed to plug in. I can plug in any number I want to as long as it's in between -1 and 1. Those are the input values. What that means is I'm not even allowed to plug in -2. I can't. It's not going to work. Okay? It's not going to work, and so this is inverse cosine function. Here we can see the graph of the inverse cosine function. We're not going to have to graph it. What we are going to have to look at is the domain. The domain of inverse cosine is the same as the domain of the inverse sine, -1 to 1. The range is not, though. The range is a little bit different. The range of an inverse cosine is from 0 to pi. Okay, you are going to need to know those, or at least be able to look them up. Okay, that's very important. Now, what you might notice is from 0 to pi. If we were in degrees, that would be like from 0 to 180. Okay, most of the time we'll be in radians, but sometimes we might be in degrees. And that's saying from 0 to 180, which would indicate we're in either quadrant 1 or quadrant 2. And so there is no 3 or 4. It's only quadrants 1 and 2. And so what you would be thinking is positive numbers would be defined in quadrant 1, and negative numbers would be defined in quadrant 2. Remember, cosine is going to be negative on the left. So second quadrant, negative values. That's what you want to remember. Okay, so it's going to be really important that you can think about the domain and the range of all of these inverse trig functions. X-intercept is at 1, y-intercept is at pi over 2, and there is no symmetry. So let's do some examples. Example 2, we're finding inverse cosine values. Find y. We've got inverse cosine, or arc cosine of 1. Arc cosine of 1. So you look at your chart, and you're looking at cosine, you're looking at 1, you're going backwards to find the angle. And that's what we're finding. When we find an inverse trig function, we're finding an angle. Inverse cosine of 1 is 0. And so we always do what and where, but the where generally indicates if it's positive or negative. And since there's no such thing as a negative 0, that's just it. Inverse cosine of 1 is 0. Don't have to worry about the where. Before moving on to part B, I'd rather do a couple of more examples of positive values. If I did something like inverse cosine of 1/2. Okay. Inverse cosine of 1/2. Find the cosine, find 1/2. And that angle would be pi over 3. That's the what. Well, we talk about where, and that comes from the fact that this is positive. Okay? If I know that's a positive value, that would indicate where I am, namely quadrant 1. Because we're looking at a domain for inverse cosine is from -1 to 1. That's what I can plug in. Okay, that's what I'm allowed to plug in. The range for inverse cosine is from 0 to pi. And so if you look at that on a graph, here's 0 and here's pi. I'm talking about quadrants 1 and 2. And so when I do the inverse cosine of 1/2, I see that's a positive value. I get a pi over 3 referencing, but in the first quadrant. And so in the first quadrant, it just is what it is. That answer would be pi over 3. Okay. If I did inverse cosine of the square root of 3 over 2. Again, you use the chart backwards to find the angle. That's what we're finding. When we do an inverse cosine, we're finding an angle. And so with pi over 6. But the fact that this is positive, a positive input value, is leading me towards the first quadrant where those positive numbers are. And so that pi over 6 just is what it is. Okay? If it was in the second quadrant, it would be something different. And that's what's going to happen on part B. Inverse cosine of negative square root of 2 over 2. You can get the what from the chart really easy. We know that has to do with the pi over 4, right? Straight from the chart. However, this negative indicates that we are in quadrant 2. We know that cosine is negative on the left side. Okay, normally we have cosine is positive over here and negative over here. But because my range is from 0 to pi, that means that there is no third and fourth quadrant. We're not even looking downstairs at all. Okay, so we're just looking at quadrant 1 or 2, and that negative is pointing me towards the second quadrant. Okay, so what I've got is a pi over 4 in that second quadrant. So we do what we always do, and that's pi. We call it 4 pi over 4. If you get a common denominator, it's just a lot easier to look at. I'm looking at pi over 4 before I get to that 4 pi over 4. And so this angle, this answer, is going to be 3 pi over 4. That's a lot trickier to me than the sine graphs, or the inverse sine ones. Okay? You can't just stick a negative in the front of it. That works when you do inverse sine, but sticking a negative in front of this one is going to get you the wrong answer. All right? So be very careful on inverse cosine. We talk about the inverse tangent function, and it's increasingly continuous on the domain. Okay, its domain is from negative infinity to positive infinity.
Okay? That means all real numbers. That means everything. That means you can plug in anything you want. Okay? That couldn't happen for sine and cosine. But now for tangent, inverse tangent, we can plug in anything we want. Its range is going to be between negative pi over 2 and positive pi over 2. Basically, that's talking about quadrants 1 and 4. We're only going to be in quadrants 1 and 4. 1 if we're positive, 4 if we're negative. Notice that this is written in parentheses instead of brackets like sine and cosine were. Basically, that means that we will never equal. And that kind of harkens back to the asymptotes that we should remember drawing when we grabbed a tangent curve, okay? It has to do with the asymptotes, but it's never going to equal pi over 2, and it's never going to equal negative pi over 2. It just has to be in between or somewhere, okay? So again, this is important. The domain and the range, very important to remember. X-intercept is 0, y-intercept is 0. We've got symmetry with the origin. That makes this an odd function. And then they talk about the asymptotes. Y equals pi over 2. Y equals negative pi over 2. Those are actually asymptotes here. Okay. So then they just kind of lump all three of the others together. You've got inverse cotangent, inverse secant, and inverse cosecant. So they don't get their own slide. They put them all three together. And they're giving you the ranges there. These are the ranges, and that's going to be important. But I think it's a lot easier to see if you look at this chart. Okay, look at this chart. Here was kind of an extra slide. I don't think you have this, but I wanted to highlight the restriction. If you're looking at the graph of sine x, we can tell it's not 1 to 1, and so that's why they've restricted it. What we've done, what you do is you restrict it to just looking at this part, and notice just that part goes from negative pi over 2 to positive pi over 2, okay? That would be the x values, but when you do an inverse, you switch x and y, and so the x values over here correspond to the y values over here. And your y values of the function, remember, this is sine x. Okay, so your y values of sine x would correspond to your x values of the inverse sine x. Okay, so anyway, I was just trying to show you the restriction. If you look at the cosine graph, okay, cosine is restricted here. If we restrict and just look at that, and now that's 1 to 1. Okay, but notice it's going from 0 to pi. Okay, so if cosine's x values goes from 0 to pi, then inverse cosine's y value goes from 0 to pi. There's your restriction. And then as for tangent, it's pretty easy to see how to restrict this. Just take one of the tangent curves and get rid of all the others. If you just took one of the tangent curves, that would be 1 to 1. Again, the domain of tangent is going to equal the range of the inverse tangent. And likewise with the range of tangent being the domain. Okay. So then this chart is really important. What I would really pay attention to the range. Okay? And there's two different schools of thought. Either you want to focus on the actual interval, or you want to focus on the quadrants involved. Maybe it's good to know both. Quadrant 1 is always going to be where we're positive, and then the second one, it's going to be negative in quadrant 4 for inverse sine. It's going to be negative in quadrant 2 for inverse cosine. Okay? The second one is always going to be where we are talking about the negative values. Quadrant 1 is always going to be positive. So when you get a positive value, it's always going to be in quadrant 1. That's going to be the easy part. But you're going to have to look at these intervals so that you know where to put down an angle for a negative input. Okay? It also helps to know that the domain values. The domain is the input, and the range is the output. But I want this chart. I want this chart until I feel comfortable. Okay? example 3, find the degree measure of theta in the following. We're finding inverse tangent of 1, okay? Inverse tangent of 1. And so you've always got two things, what and where. If we look at the chart, okay? Look at the chart for where tangent is going to give you 1. Remember, tangent is sine over cosine, so sine over cosine. We're trying to get 1, so I'm looking at the square root of 2 over 2 divided by itself. Okay? So that would be pi over 4 or 45. Okay? That's a 45. Since we're in degrees, that's a 45. All right? So that's what you want to do. It's kind of subtle, but you always want to remember the domain and the range. Domain for inverse tangents is, I believe that's all real numbers. So that means you can plug in anything you want. The range is from negative pi over 2 to positive pi over 2. To me, the way I look at this is I'm allowed to have a negative answer. Okay? If I'm allowed to have a negative answer, maybe that makes it easier. I don't have to think quite as much. But I know this means from negative pi over 2 down here to positive pi over 2 up here. Okay? That's quadrants 1 and 4. Okay? Or if we're in degrees, that's from negative 90 degrees to positive 90 degrees. Okay, negative 90 is down here, positive 90 is up here. We're in the first and fourth quadrant. Okay? But I don't really need all that stuff. The fact that this number 1 was positive tells me that I have to be located in quadrant 1. I know that that means quadrant 1. So when you think about the what and the where, okay, that 45 degrees in quadrant 1, 45 degrees in quadrant 1 just is what it is. This answer is 45. Okay? This answer is 45. So let's think about what it would have been if I had done inverse tangent of, let's do like square root of 3. Okay? Square root of 3. So when you look in the chart, square root of 3 is coming from this. Square root of 3 over 2 over 1/2. Those 2's cancel out, and you get the square root of 3. And so you're looking at 60 degrees, right? 60 degrees, okay? And so if that's a positive square root of 3, then that tells me that this is in quadrant 1. And 60 degrees is just 60 degrees, okay? However, if that was a negative, if I had said like tangent, inverse tangent of negative square root of 3, you're still looking at your 60 degree reference, but that negative right there tells you that it's in quadrant 4. Quadrant 4, because that's where we're defined over here. Quadrants 1 and 4, but when we're negative, we're in quadrant 4. Okay? And so the way I look at it is I'm allowed to have a negative answer. If I'm allowed to have a negative answer, then you can just stick a negative in front, and the answer is negative 60 degrees. That won't always be the case. Okay? But with this one, since it's defined from negative pi over 2 to positive pi over 2, or from negative 90 to positive 90, that's the case. All right. So part B, I'm looking at inverse secant of 2. Of course, we don't have that in our chart. It's hard to do the reciprocal functions like secant, cosecant, and cotangent. And so what we would do is look at the reciprocal function. Secant is the reciprocal of cosine. So let's try inverse cosine of 1/2. You take the reciprocal. The reciprocal of secant is cosine, and the reciprocal of 2 is 1/2. And so I'm looking at secant, and so what's the domain and the range of secant, or inverse secant rather? The domain is this weird from negative infinity to negative 1 union with 1 to positive infinity. And what that means is anything else besides what's in between negative 1 and 1. Okay, it can't be between negative 1 and 1, it has to be outside of that. And so that means that my 2 right here is okay, that's fine. I'm allowed to plug in a 2. That's the domain. The range for inverse secant is from 0 to pi. Or in this case, from 0 to 180 degrees. Okay? And so when you look at that, in 0 to pi, it's talking about quadrants 1 and 2. And if it's positive, we'd be in quadrant 1, and if it's negative, we put it in quadrant 2. And so
you look at the inverse cosine of 1/2, and we just look at the chart. Inverse cosine is 1/2. It goes to a 60-degree angle, right? 60-degree angle. So that's the what that I get from the chart. But the fact that this was a positive number tells me that I'm in the first quadrant. Okay? It's 60 degrees in that first quadrant. Okay? It's 60 degrees in that first quadrant. And so it just is what it is. It's 60 degrees. Okay? Now, if that had been inverse secant of -2, and we did the reciprocal function inverse cosine of -1/2, that's going to be a little bit different. Okay? That's going to be your 60-degree reference angle. Okay? The what is still the same. You're still getting that 60 degrees from the chart. But since this is defined in quadrants 1 and 2, that negative value tells me that I'm in quadrant 2. I know I'm in quadrant 2. And so what that's going to require is to put a 60-degree reference in quadrant 2, and that's not -60. That's not -60. That's 60 degrees before you get to 180. That's 120 degrees. So you have to be careful on some of these, I think. Example 4, find y in radians if y equals inverse cosecant of -3. I think this is a little bit harder to start with, so I'm going to start with an easier one. Let's try inverse cosine of 0.4. Okay? Let's find the inverse cosine of 0.4, and we want to do it in radians. So let's just make sure we're in radians. And all we'd have to do is type in inverse cosine of 0.4. And that gets us 1.159, let's say. So that's 1.159. Okay, so that's the what. What we'd have to look at is look at the range for inverse cosine. The range for inverse cosine is from 0 to pi. And so that means that this is defined from 0 to pi. That means first or second quadrant. And basically, any positive value, when this is positive, this 0.4, if that's positive, that's going to put us in the first quadrant. And since that 0.4 is positive, we know we're in the first quadrant. And so when we do what, the calculator gives us what? 1.159, but we have to look at the where and think about this as being in that first quadrant. It's in the first quadrant, and the good thing about first quadrant is it just is what it is, and so that's the answer. If we had done a negative 0.4, that would have put us in the second quadrant. Okay, and so if you think about what's going to happen in the second quadrant. Okay, let's just use our calculator and see what happens. So we've got inverse cosine of -0.4 gives us 1.982. 1.982. 1.982. Now that seems like it's different. That seems a little bit confusing, but it really should be the same kind of result. That 1.159 is kind of like a reference angle. And if you remember, pi is 3.14. If we took pi and subtracted that 1.159, that should give us our 1.982. And so we're looking at 1.982 as the answer, but you can find it using either this or just looking straight at the calculator. Okay, so let's try one. Let's try one that's in degrees. If I did inverse cosine of -0.6, and I want the answer in degrees. Make sure we're in degrees. Just type it in, inverse cosine -0.6, 127 degrees or so. Let's just call that 127 degrees. And that puts us into the second quadrant. That's where we need it. Okay, of course that's in the second quadrant. We knew that was going to be in the second quadrant when that number was negative. So there still is this concept of what and where. But now, let's look at the original problem. It says find y in radians if y equals inverse cosecant of -3. Well, we don't have an inverse cosecant button. So what we're going to do is take the reciprocal. Reciprocal of cosecant is sine. So let's look at the inverse sine of -1/3. Take the reciprocal. We can plug this in the calculator. We need to be in radians. But we're going to do inverse sine of -1/3. And that gives us this value, okay? -0.3398. -0.3398. Now don't forget, you need to look at your range. And for inverse cosecant, the range is from -π/2 to +π/2. So what I like to do is I just look at it and say, am I allowed to have a negative number? And since the range goes from -π/2 to +π/2, or quadrants 1 and 4, I'm allowed to have a negative number. I'm allowed to have a negative answer. That's what's going to put me into that fourth quadrant. So since I'm allowed to have a negative answer, I'm going to circle it. That's it. So then the next one wants the degrees of arc cotangent or inverse cotangent. To do this, I'm also going to take the reciprocal function, inverse tangent of this reciprocal. And so if you're looking at your calculator, this one wants degrees. So inverse tangent of 1 over -0.3241 would be -72. Okay, -72 degrees. Let's just estimate. Okay, but I think the question always has to be, am I allowed to have negative answers? And so when you look at the range for inverse cotangent, the range for inverse cotangent is from 0 to pi. And what that's telling me is my output is not allowed to be negative. If we were in degrees, maybe it's easier to understand. In degrees, that's from 0 to 180. 0 to pi, same thing, 0 to 180. I'm not allowed to have a negative answer. My answer has to be in between 0 and 180. So, think about where we are. From 0 to 180 means we're in quadrant 1 or 2. But the negative, the negative is going to happen in the second quadrant here. That's where, tangent, cotangent, or negative is in that second quadrant. And so you should really just look at this as a 72-degree reference angle. It's a 72-degree reference angle in that second quadrant. And so what angle is that? Well, you would find that because it's 72 degrees before you get to 180, or 180 minus 72 is 108. This answer, 108 degrees. Example 5. We're going to evaluate this. It says sine of inverse tangent of 3/2. And what you need to understand is that this inverse trig function is talking about an angle. So understand that that part is an angle, and so it's like we want sine theta is basically what we want, okay? We want sine of some angle. And so let's draw a picture of this angle, okay? So for tangent, I know tangent is defined in quadrants 1 and 4. Remember the range? The range for tangent was -π/2 to +π/2, which is defined in quadrants 1 and 4, okay? It's defined in quadrants 1 and 4. From -π/2 down here to +π/2 up here, that's defined in quadrants 1 to 4. So the fact that this is positive, 3/2, okay, means that, all right, if you're in quadrant 1 or 4, the positives are upstairs and the negatives are downstairs here, okay? And so the fact that that 3/2 is a positive number would indicate that I'm in quadrant 1. And so I'm going to draw this angle in quadrant 1. I think that's the hard part. Being able to determine that we have an angle in quadrant 1, I think that's the hardest part of this. So if you've got some angle, and we called it theta, so label your angle. I'm seeing some students that are not labeling their angles. It makes it harder on you, I think. And then the tangent ratio, we know tangent is y over x. So the tangent ratio, y over x, is 3/2. So that's the y number and the x number, 3/2 right there. We should be able to do Pythagorean theorem to find the hypotenuse. 2 squared plus 3 squared equals c squared, or r squared, I guess. That's 4 plus 9 is 13. But 13 equals c squared. This is going to be the square root of 13. That hypotenuse is square root of 13. Okay. Now here's why this is so easy. Remember when I wrote down that we're finding sine theta? Just look at your picture. You ought to be able to look at the picture and tell me what sine theta is. Just look at the ratio. You know the sine ratio is y over r. So look at your y over your r number. Your sine ratio is 3 over square root of 13. At which point all we would do is rationalize the denominator in the usual way. We have 3 square root of 13 over 13. And that's the answer. Okay? So I think the hard part is just knowing where to draw your picture. So if I look at part B, it's tangent of inverse cosine of negative 5/13. Now again, this is an angle. So if you think of that as an angle, theta, we're just finding tangent theta. Okay? But we need to draw a picture of this angle. So, look at inverse cosine. And the range for inverse cosine was from 0 to pi. So it's really important that you can figure out the ranges. Okay? So if we're from 0 to pi, that's talking about quadrants 1 and 2. But what you're going to notice is this negative right here, that's a negative number. And so what quadrant is this angle going to be located in? Second quadrant, because that's where the negative numbers would be. Okay? So the fact that that's a negative 5/13 is indicating that we are in quadrant 2. So let's draw a picture. Let's draw our picture in quadrant 2. We've got some angle taking us into quadrant 2. But we're going to form a triangle out of that. And label that, label that theta. Just go ahead and label it. People aren't labeling it. But we've got the cosine ratio of negative 5/13. Okay, remember cosine ratio is x over r. And so your x, let's call that negative 5, and your r is 13. So you've got that cosine ratio of negative 5/13 in the second quadrant. We need to find the missing side. Okay, the missing side right here, and some of you might already know it because this is one of the special patterns that comes up all the time. But if you don't know it, you're going to say something like y squared plus negative 5 squared is 25 equals 13 squared and 169. I'm just doing the Pythagorean theorem basically. Subtract, and that's 144. Square root, you're going to get plus or minus 12. But in the second quadrant, we know y numbers are positive. So that's positive 12. Okay? So we've got all the hard work done. All we need to do is find this tangent ratio. Tangent theta, remember the ratio for tangent is y over x. So you look at your y over your x, y over x is going to be 12 over negative 5, or negative 12 fifths. Example 6a, we're evaluating another expression. I think this looks really super complicated. Okay? It looks really tough. But what's important to remember is that when you see an inverse trig function like this, that's an angle. And here's another inverse trig function, so that's going to be another angle. And so what I would recommend that you do is just call this one something and call this one something else. And so what I've got there is two different angles, angle A and angle B. You could use theta and beta if you want. You could use Greek letters, I suppose, but probably going to be more familiar to you if you use A and B here. But I've got angle A and I've got angle B. And so if you look at what you have at this point, that should look familiar to you. You've got a cosine sum, and I see some of you looking at the formulas right now. That's smart, okay? This should remind you of one of those identities on the board right now. You've got a cosine sum. And so look at the cosine sum formula. Find the cosine sum formula. It says cosine of the first one, cosine of the second one, minus sine of the first one, sine of the second one. So we've seen this problem before. We've done this, I forget if this was section 7.3 maybe, but we had 4 holes to fill in. And that's what we're going to have to do. We're going to have to fill in those 4 holes and then simplify. Okay? But go back to what I've written in red there. We understand that an inverse tangent is an angle. So let's draw a picture of that angle. What you want to do is you want to remember where inverse tangent is defined, and that comes from the range. And so the range on an inverse tangent is from negative pi over 2 to positive pi over 2. In other words, yeah, you did. So we are in quadrants 1 and quadrant 4. Okay? Quadrant 1 and quadrant 4. And so when you look at this ratio, I know it doesn't look like a ratio, but square root of 3, we call that square root of 3 over 1. My ratio is a positive value. And the positive values are always going to be in the first quadrant. Okay? So when I see this, I see that positive value. I see it's going to be in the first quadrant. I'm going to draw a picture of that angle in the first quadrant. This is angle A. Make sure you label it. I'm seeing a lot of students that aren't labeling their angles. Make sure you label this. Okay? Tangent, inverse tangent, we know that the tangent ratio is y over x. So your square root of 3 over 1, let's label that y over x right there. And then we can do Pythagorean theorem to figure out the missing side. And at some point you're going to be able to do this in your head, I think, but we do 1 squared plus square root of 3 squared equals c squared r squared. That's 1 plus 3, that's 4. And so square root, we know that hypotenuse is going to be 2. That missing side is 2. All that was Pythagorean theorem. So once you've got all those sides, then you ought to be able to tell me any of the trig ratios. And you look at your 4 blanks that you have to fill in. It looks like we need to know what cosine A is. We need to know cosine A, and we need to know sine A. And you ought to be able to tell those from this picture. Look at the picture, look at the angle, look at the relationships to the sides. The cosine ratio, x over r, that's going to be 1/2. The sine ratio, y over r, is going to be square root of 3 over 2. And so I should be able to fill in those 2 spots based off of my picture. Okay? That's all I can tell about angle A, and so I can't fill in those other blanks. I'm going to need to draw a different picture of angle B. And so you look at arc sine. Arc sine, we want to know where to draw it. Remember the range for inverse sine there is this. But again, that's talking about quadrants 1 and quadrant 4. 1 if you're positive, 4 if you're negative. And so when I see that this 1/3 is positive, that's directing me towards that first quadrant. And so I'm going to draw a picture of angle B in that first quadrant. Again, label it. Arc sine 1/3. I've got the sine ratio is 1/3. That's y over r. So y over r, I've got those 2 sides, and I can find the missing side using Pythagorean theorem. I'm going to do x squared plus 1 squared equals 3 squared. That's x squared plus 1 equals 9. Subtracting, you get x squared equals 8. And so square root, we're looking at the square root of 8, plus or minus. Plus or minus. Okay? But over there on the right, first quadrant, we're talking about a positive x value, so that's going to be the square root of 8. Square root of 8 there. Okay? That's probably a good idea to simplify that square root. That's square root of 4 times square root of 2, or 2 square root of 2. Okay? So when you need the cosine ratio, cosine B right here, cosine is going to be x over r. We're going to call that 2 square root of 2 over 3. And then your sine ratio is y over r, that's 1/3. And so all that's left is I'm going to simplify my fractions and stuff. So I've got over on the left here 2 rad 2 over 6 minus square root of 3 over 6. I've got 2 radical 2 minus square root of 3 over 6. And that's it. Example 6b, we've got tangent of 2 arcsine 2/5. What I want you to realize is this arcsine, this inverse trig function, is an angle. So if you think of that as angle A, then maybe it's a little bit more obvious what's going to happen. We have tangent of 2A, or tangent of 2 times the angle. It's a double angle identity. So hopefully that makes you want to look over at the formulas, look them up on the formula sheet or up on the board. Tangent 2A is equal to 2 tangent A over 1 minus tangent squared A. So we're going to utilize that identity, but first we're going to draw a picture of the angle. Okay, this is an angle. And so we look at inverse sine, and we know the range of inverse sine is from negative pi over 2 to positive pi over 2. But that means that it's defined in quadrants 1 and 4. So we're either going to have a picture of an angle in quadrant 1 or a picture of an angle in quadrant 4. And so you should notice that this is a positive fraction, that the 2/5 is a positive ratio. And what that's going to do is that's going to tell me that I'm in the positive realm. We're in quadrant 1, not in quadrant 4. And so what I ought to be able to do is draw a picture of that angle in quadrant 1. So let's do that. We're going to have an angle, and I'm going to label it angle A in quadrant 1. And we see the sine ratio here. The sine ratio is 2/5. So we know that sine ratio is y over r. And that gives me 2 of my sides of my triangle, the y side and the r side, 2 and 5. And so we use Pythagorean theorem like we always do. X squared plus 2 squared equals 5 squared. X squared plus 4 equals 25. Maybe you can do this in your head. But you're getting x equals plus or minus square root of 21. But since we're in the first quadrant, we know that's going to be the positive version. Square root of 21 right there for that missing side. Once we have all 3 sides of that triangle, you should be able to give me any of the 6 trig ratios that I asked for. We know an awful lot about angle A at this point. But when we look at our formula, we want the tangent ratio. And so we know the tangent ratio is y over x. And so you look at your y over x, it's going to be 2 over square root of 21. Tangent A is 2 over square root of 21. So we've got this expression, and the rest is just going to be algebra we clean up. Okay, so cleaning up our fraction a bit, 2 times 2 over square root of 21 is going to be 4 over square root of 21. And then on the bottom, we've got to square that quantity, but that's actually good because that's going to make the square root go away. We'll have 1 minus 2 over 21. At which point we're subtracting fractions, and we see this all the time. If we're subtracting fractions or adding fractions, we need a common denominator. So let's call that 1. Let's call that 21 over 21. Oh, I have a mistake. I forgot to square that too. That's actually going to be 4 over 21. When I square that 2 over square root of 21, that's 4 over 21. Okay, but I get a common denominator. I'm going to have 21 over 21, and that's going to equal 4 over square root of 21, all over 21 minus 4 is 17 over 21. Every time I get a problem where I divide fractions, I'm going to multiply by the reciprocal. So if I multiply the reciprocal, I'm going to have 4 times 21 over 17 square root of 21. And you can multiply 4 times 21 and get 84 if you want, but I know what's going to happen when I rationalize this denominator, and so I'm leaving it. You rationalize the denominator in the usual way, multiply by square root of 21 over square root of 21, and that turns into 21. And so I have a situation where it looks like I can cancel those 21. 21 cancels the 21, and I'm looking at 4 times the square root of 21 over 17. I think the hardest part about this is just cleaning up all the algebra, but we're doing fractions, we combine like terms or get a common denominator, we multiply by the reciprocal, we rationalize the denominator. We do the same kind of algebra stuff that we always do. Example 7a, we're writing a function in terms of u. This one's going to seem harder, I think, because there aren't any numbers. But it could be easier because there aren't any numbers. It just kind of depends on your attitude, I suppose. But again, we look at this and understand that that's an angle. Okay, so you can call that a or theta or whatever. We're going to have sine theta at some point. But what I want to do is I want to draw a picture of that angle. Draw a picture of angle theta. Now, the thing that's tricky about this is we know that tangent theta is defined, or its range is from negative pi over 2 to positive pi over 2, which puts us in either quadrant 1 or 4. Now, because that u is a variable, I don't know at this point if u is positive or negative. So really, we don't really know if that's in the first or fourth quadrant, but it turns out that it doesn't matter because it's a variable. It's gonna work out the same either way. So let's just draw it in the first quadrant. Okay. And so if you think about it, it doesn't matter that we don't have numbers. It doesn't matter. You've got the tangent ratio is u over 1. And so we know tangent is y over x. So let's draw our picture. We want to draw a picture of theta in the first quadrant. Okay, this will also work if you draw it in the fourth quadrant, but I'm going to draw it in the first quadrant. The tangent ratio y over x is u over 1. So let's just do u over 1 right there. There's my y over my x. And then we have to do Pythagorean theorem to find that missing side. So a squared plus b squared equals c squared, or r squared if you want. And so, what I've got is u squared plus 1 equals c squared. In order to solve, I'm going to take the square root of that. C is going to equal the plus or minus square root of u squared plus 1. I know that's an ugly looking expression, but that's what we've got. And so since the radius here, or the hypotenuse, will never be a negative number, we just know that's going to be just regular square root of u squared plus 1. That's your hypotenuse. Square root of u squared plus 1. And so I've done the hard part. All you have to do is find the sine ratio. We're finding sine theta, and so sine theta is y over r. So look at your picture. Look at your angle theta, and the ratio for y over r is u over square root of u squared plus 1. That's y over r. That's the sine ratio. And so we do what we always do. We rationalize the denominator. And that gets me this big old mess up on the top. U times the square root of u squared plus 1. On the bottom, the square root goes away. You can combine those. You get just regular u squared plus 1. And that's it. So maybe that's easier than having numbers. We didn't have to do a whole bunch of algebra and stuff with the numbers. So let's look at 7b. It's pretty much the same thing. Okay, we're writing an expression in terms of u. But again, look at your inverse trig function here and understand that that's an angle. You call it a or theta or whatever, it doesn't really matter. If you understand that that part is an angle, you're going to recognize cosine 2a, which would force you to look at your formulas probably. I don't know if you know these or not, but that's a double angle cosine. And so you look at your double angle cosine identities, and you see that there are three different possibilities. So we're going to have to pick one, but let's hold off on that. We'll pick one later. Let's draw a picture of angle A. Again, for inverse sine is defined, or its range is from negative pi over 2 to positive pi over 2. Again, that puts us in either quadrant 1 or quadrant 4. And it'll work for either one, but let's just stick to quadrant 1. I'm going to draw my picture in quadrant 1. And so we're drawing a picture of our angle A, label it, in quadrant 1.
And notice what we have. We have the sine ratio. Inverse sine is u, so we'll call that u over 1. But my sine ratio is u over 1. So that's the y side over the r side, right? Y over r is u over 1. And so again, I'm going to do Pythagorean. You go like x squared plus u squared equals 1 squared. Subtract u squared over, you'll have x squared equals 1 minus u squared. And then take the square root. X is going to equal plus or minus square root of 1 minus u squared. But since we're in the first quadrant, we'll use the positive version. And so this missing side, this x side, is the square root of 1 minus u squared. So I'm finding the cosine ratio. Okay, I'm finding the cosine ratio. So let's look at one of my 3 double angle identities. Maybe we use 1 minus 2 sine squared a. Okay, I just picked one. If you look at that, that's 1 minus 2 times the sine ratio squared. Okay. It turns out that this was easier than I even made it, because you could have told me the sine ratio without drawing this picture. Okay? Look at the picture and tell me what the sine ratio is. It's u over 1, right? It's u over 1, but maybe we could have told that, just from looking at the problem. The sine ratio is u over 1, of course it is. Okay? And so what I have then is 1 minus 2 u squared. That's it.